Listening practice, a detailed expansion of Chapter 1, Introduction to Reinforced Concrete for your book, structured to provide clarity and depth while maintaining readability. Chapter 1, Introduction to Reinforced Concrete 1.1 History and Development, Early Use of Concrete, Roman Contributions, e.g., Pantheon, aqueducts, with lime-based concrete. Reinforcement Evolution, 19th Century Innovations, Joseph Monier's patented reinforced flower pots, François Coignet's iron-reinforced concrete. 20th Century Standardization, Introduction of Portland cement, high-strength steel. Modern advances, high-performance concrete, HPC, fiber-reinforced concrete, and 3D printed structures. 1.2 Advantages and limitations. Advantages, high compressive strength and durability. Flexibility in shaping, moldability. Fire and weather resistance. Synergy of steel, tension, and concrete, compression. Limitations, low tensile strength, requires reinforcement. Cracking due to shrinkage and thermal effects. Heavy weight compared to steel or timber. Construction complexity, formwork, curing. 1.3 Basic components and materials. 1. Concrete, composition, cement, aggregates, coarse/fine, water, admixtures. Grades, normal, M20 M40, high strength, M50+, lightweight, and self-compacting concrete. 2. Reinforcement, types, mild steel, Fe 250, HYSD bars, Fe 415, Fe 500, epoxy-coated bars, stainless steel. Forms, rebars, welded mesh, pre-stressing tendons. 3. Composite action, bond strength between steel and concrete. Role of cover in corrosion protection and fire resistance. 1.4 Key terminology, workability, slump test, compaction factor. Curing, moisture retention for hydration. Cover, minimum concrete cover to prevent corrosion, as per codes. Key features to enhance the chapter, case study, iconic RC structures, e.g., Burj Khalifa, Hoover Dam. Diagram, stress-strain curve of concrete versus steel. Comparative table, RC versus steel/masonry in cost, strength, and lifespan. Learning outcomes. By the end of this chapter, readers will, 1. Understand the historical context of reinforced concrete. 2. Recognize its pros/cons compared to other materials. 3. Identify core components and their roles in structural behavior. Let me know if you'd like to refine any section or add design examples/illustrations. Chapter 2, Material Properties of Reinforced Concrete. This chapter covers the key properties of concrete and steel, their mechanical behavior, and how they work together to form a strong, durable composite material. 2.1 Concrete, Strength, Durability, and Elasticity. 2.1.1 Strength of concrete, compressive strength, F. Definition, maximum load-bearing capacity under compression, measured in MPa or Psi. Testing, standard 28-day cube/cylinder test, is 516, ASTM C39. Grades, M20, M25, M30, etc., where the number denotes MPa strength. Tensile strength, low, 10% of compressive strength. Measured via split tensile test, is 5816, or flexural test. Factors affecting strength, water-cement ratio, Abrams law. Curing conditions, admixtures, and aggregate quality. 2.1.2 Durability of concrete, key durability concerns, permeability, resistance to water/chemical ingress. Carbonation, reduces alkalinity, leading to corrosion. Chloride attack, marine environments. Freeze-thaw damage, in cold climates. Improving durability, use of low W/C ratio, pozzolanic materials, fly ash, silica fume. Proper cover thickness and corrosion inhibitors. 2.1.3 Elasticity and creep. Modulus of elasticity, E, depends on strength, e.g., is 456:2000 gives backslash, E underscore C equals 5000 backslash SQRTF underscore CK backslash. Creep, long-term deformation under sustained load. Effects, increases deflection, reduces pre-stress force. 2.2 Reinforcing steel, types and mechanical properties. 2.2.1 Types of reinforcement type grades, is 1786, characteristics mild steel, Fe 250, yield strength, 250 MPa low strength, high ductility HYSD bars, Fe 415, Fe 500, 415/500 MPa high strength, ribbed for bond TMT bars, thermomechanically treated, Fe 550 plus enhanced strength and corrosion resistance pre-stressing steel high tensile. 1650 to 1860 MPa, used in precast/PSC structures. 2.2.2 Mechanical properties, yield strength, F_Y stress at which steel permanently deforms. Ultimate strength, F_U maximum stress before failure. Ductility, elongation, percent, before fracture, critical for seismic zones. Bond strength, ribbed bars improve adhesion with concrete. 2.3 Stress strain behavior of concrete and steel. 2.3.1 Concrete stress strain curve, elastic phase, linear up to 30% of F. Plastic phase, microcracking begins, curve becomes nonlinear. Peak stress, F maximum compressive strength. Post-peak behavior, rapid strength drop, brittle failure. 2.3.2 Steel stress strain curve, elastic phase, linear, Hooke's law, backslash, E_S equals 2 backslash times 10⁵ backslash, MPa backslash. Yield plateau, constant stress with increasing strain. Strain hardening, stress increases until ultimate strength. Fracture, occurs at 15-20% elongation, ductile failure. 2.3.3 Composite behavior, perfect bond assumption, strain compatibility, concrete and steel deform equally. Cracked versus uncracked sections, uncracked, both materials resist load. Cracked, steel carries tension, concrete carries compression. Key takeaways for designers: concrete is strong in compression but weak in tension. Steel provides tensile strength and ductility. Stress strain curves define material limits and failure modes. Durability depends on mix design, exposure conditions, and detailing. Illustrations and tables to include 1. Graph, comparative stress strain curves for concrete and steel. 2. Table, concrete grades and typical applications. 3. Diagram, bond mechanism between rebar and concrete. Would you like a worked example on calculating modulus of elasticity or interpreting stress strain data? Let me know how to refine this further. Chapter 3, Design Philosophies and Codes. This chapter explains the fundamental design approaches for reinforced concrete structures and introduces major international codes like ACI, American, Eurocode, European, and IS, Indian, standards. 3.1 Working Stress Method, WSM, Concept and Assumptions, Principle, stresses in concrete and steel remain within elastic limits under service loads. Assumptions, linear stress strain behavior, Hooke's law. Perfect bond between steel and concrete. Uncracked section behavior, ignores concrete in tension. Key equations, modular ratio, M/M equals frac E_SE_C where E_S equals steel modulus, E_C equals concrete, stress calculation, F_C equals frac MI_CR /y quad text, concrete, F_S equals M_F_C quad text, steel, Modulus, advantages and limitations. Simple calculations for low-risk structures. Overly conservative, doesn't account for plastic behavior. Not used in modern codes, replaced by limit state design. 3.2 Ultimate limit state, ULS, design concept and philosophy. Objective, ensure safety against collapse under maximum loads. Load factors, dead load, 1.5, live load, 1.5-1.6, wind/seismic, 1.2-1.5. Material factors, concrete, 0.67-0.8, steel, 0.87-0.9. Design checks 1. Flexural capacity, \m_u equals 0.36 \f_c_k \b \x_u d 0.42 Shear capacity, \v_u equals v_c plus v_s /quad \text, concrete plus steel contribution, \advantages economical, uses material strength more efficiently. Accounts for ductility and redundancy. 3.3 Serviceability limit state, SLS, design key checks 1. Deflection control, limits, \frac span 250 for beam/slabs. 2 Crack width control, max allowable, 0.3 mm, normal, 0.2 mm, aggressive environments. 3 Vibration and durability, ensures long-term performance under service loads. Methods, elastic analysis, for deflection. Crack width formulae, e.g., Gurgley-Lutz equation in ACI. 3.4 Overview of major design codes 1. ACI 318, American Concrete Institute, Philosophy, Strength-Based, ULS, plus Serviceability checks. Key features, load combinations, e.g., \1.2D plus 1.6L \. Strut and tie model for deep beams. 2 Eurocode 2, and January 1, 1992, Philosophy, Limit State Design, Partial Safety Factors. Key features, characteristic versus design strengths. Explicit durability requirements. 3 is 456, Indian Standard, Philosophy, blend of WSM, old, and limit state, current. Key features, MIN reinforcement rules. Special provisions for seismic zones, is 13,920. Comparison table parameter ACI 318 Eurocode 2 is 456 safety factor, concrete, 0.65 0.85 0.85, FCK/1.5, 0.67, FCK/1.5, max crack width 0.4 mm, normal, 0.3 mm 0.3 mm load combos 1.2D plus 1.6L 1.35D plus 1.5L 1.5D plus 1.5L Key takeaways WSM is outdated but useful for understanding basics. ULS ensures safety against collapse. SLS guarantees usability and durability. Codes differ in factors but share core principles. Illustrations to include 1. Flowchart, ULS versus SLS design process. 2 Graph, load deflection curve showing service versus ultimate states. 3 Case study, comparison of beam design in ACI versus Eurocode. Would you like a worked example comparing ACI and IS code designs? Let me know how to refine this further. Chapter 4, Design of Reinforced Concrete Beams. This chapter covers the step-by-step design process for RC beams, including flexure, shear, torsion, and serviceability checks, following limit state design, IS 456/Eurocode/ACI. 4.1 Flexural Analysis and Design. 4.1.1 Basic Principles, Assumptions, Plane sections remain plane, Bernoulli's hypothesis. Perfect bond between steel and concrete. Concrete tensile strength equals 0, after cracking. 4.1.2 Design steps for singly reinforced beams. 1. Calculate factored moment, mu, \m_u equals 1.5 \m service quad, text as per is 456, \2. Determine limiting moment, mu lim, \m_u lim equals 0.36 \f_ck b .x_u d 0.42 x_u where x_u equals depth of neutral axis. 3. Check if m_u lec m_u lim singly reinforced, else doubly. 4. Calculate steel area, AST, \a_st equals frac m_u 0.87 f_y d 0.42 x_u reinforced. 4.1.3 Doubly reinforced beams, when m_u lim compression steel, \a_sc is added. Formulae, \a_sc equals frac m_u lim 0.87 f_y d d \a_st equals a_st1 for m_u lim plus a_st2 for extra moment. \_4.2 Shear and torsion design 4.2.1 Shear design 1. Calculate factored shear force, Vu. 2. Check concrete shear capacity, Vc, \v_c equals 0.12 \sqrt f_ck b .d 3. If v_u_v_c provide shear reinforcement, stirrups, frac a_svs_v equals frac v_u, v_c 0.87 f_y d where s_v equals stirrup spacing. 4.2.2 Torsion design, torsional moment, 2, is combined with shear and bending. Equivalent shear, VE, \v_e equals v_u plus 1.6 frac t_ub reinforcement, closed loop stirrups plus longitudinal bars. 4.3 Deflection and crack control 4.3.1 Deflection checks, permissible deflection, as per is 456 \delta_max equals frac span 250 quad, text for beams, effective depth, d, control, frac ld lec 20 quad, text for simply supported beams, 4.3.2 Crack width control, Gurgley-Lutz equation, ACI W_max equals 0.076 beta f_s sqrt 3d_c where W_max equals crack width, f_s equals steel stress, is 456 provisions. Max crack width equals 0.3 mm. Normal, 0.2 mm, severe exposure. 4.4 Detailing requirements 4.4.1 Reinforcement rules, minimum steel, AST min \a_st min equals frac 0.85 b df_y maximum steel, AST max 4% of cross-section 4.4.2 Anchorage and lap splices, development length, LD \L_D equals frac 0.87 f_y /54 tau_BD where \tau underscore BD equals bond stress, dash key takeaways singly reinforced beams for M underscore U lec M underscore U lim doubly reinforced beams for higher moments. Shear stirrups required if V underscore U V underscore C deflection and crack control ensure serviceability. Dash illustrations and examples to include 1. Flowchart, beam design process, flexure shear detailing. 2. Example, full design of a simply supported beam, is 456. 3. Comparison, singly versus doubly reinforced beam cross sections. Would you like a worked example for a real-world beam design? Let me know how to refine this further. Chapter 5, Design of Reinforced Concrete Slabs. This chapter covers the analysis and design of different slab systems, including one-way, two-way, flat slabs, and ribbed slabs. Following is 456, ACI 318, and Eurocode standards. 5.1 one-way and two-way slabs. 5.1.1 one-way slabs. Definition: slabs supported on two opposite sides, L/B2. Load transfer, primarily in the short direction. Design steps: 1. Calculate factored load, dead and live. 2. Determine bending moment, for unit width \M underscore U equals \frac W underscore U \L28 quad, \text simply supported, \3. Design reinforcement, similar to beams but per meter width. 4. Check deflection and cracking. 5.1.2 Two-way slabs. Definition: slabs supported on all four sides, L/B less than or equal to 2. Load transfer, bidirectional, using Rankine-Grashof or is 456 coefficients. Design methods: coefficient method, is 456, uses moment coefficients based on edge conditions, fixed/simply supported. Yield line theory, for ultimate strength analysis. 5.2 Direct design and equivalent frame methods, for two-way slabs. 5.2.1 Direct design method, ACI 318, conditions, minimum 3 continuous spans. Slab panels must be rectangular. Steps: 1. Divide slab into column and middle strips. 2. Distribute moments, positive/negative, as per code. 5.2.2 Equivalent frame method, used for irregular slabs or those with openings. Process: model slab beam column as a 2D frame. Analyze using stiffness methods, software like ATABS. 5.3 Flat slabs. 5.3.1 Key features: no beams, direct transfer of load to columns. Components: drop panels, thickened slab near columns. Column heads, to reduce shear stress. 5.3.2 Design steps. 1. Check punching shear, \tau underscore V equals \frac V underscore UB underscore 0 \d lec \tau underscore C quad, text per is 456, \2. Moment distribution, similar to two-way slabs. 5.4 Ribbed slabs. 5.4.1 Advantages: reduce self-weight, voids between ribs. Economical for long spans, 6 m. 5.4.2 Design approach. 1. Rib design, treated as T-beams, flange equals topping slab. 2. Topping slab, minimum 50 mm thickness. Designed for local bending. Key takeaways: one-way slabs bend in a single direction, L/B2. Two-way slabs require bidirectional reinforcement, L/B less than or equal to 2. Flat slabs need punching shear checks at columns. Ribbed slabs optimize weight for long spans. Illustrations and examples. 1. Diagram: load distribution in one-way versus two-way slabs. 2. Table: moment coefficients for two-way slabs, is 456. 3. Case study: flat slab design with drop panels. Would you like a worked example for a two-way slab using the coefficient method? Let me know how to refine this further. Chapter 6, Design of Reinforced Concrete Columns. This chapter covers the analysis and design of RC columns, including axial, uniaxial, and biaxial loading, with emphasis on short versus long columns and interaction diagrams. 6.1 Axial and eccentric loading. 6.1.1 Axially loaded columns, pure compression, no bending moment, design strength, is 456, /p_u equals 0.4 f_ck_c plus 0.67 f_ya_sc /a_c equals concrete area, /a_sc equals steel area. 6.1.2 Eccentrically loaded columns, uniaxial bending, moment about one axis, eccentricity, E, /e equals /frac m_up_u failure modes, crushing, large /e buckling, small /e -6.2 Short versus long columns. 6.2.1 Short columns, slenderness ratio, lambda, lambda equals /frac L_EFFR /lec12 /quad, text is 456, L_EFF equals effective length, R equals least radius of gyration, design, governed by material strength, not buckling. 6.2.2 Long columns, slenderness ratio, lambda, lambda 12 /quad, text buckling additional moment, P delta effect, m_at equals P_u delta equals lateral deflection risk, -6.3 Biaxial bending and interaction diagram. 6.3.1 Biaxial bending, load application, moments about both x and y axes. Is 456 Approach, Bressler's reciprocal load method /frac 1p_uxy equals /frac 1p_ux plus /frac 1p_ui, /frac 1p_u0 /p_ux, p_ui equals uniaxial capacities, p_u0 equals pure axial capacity. 6.3.2 Interaction diagrams, purpose, graphical representation of axial load versus moment capacity. Key points, pure axial load, P, balanced failure, P, M, pure flexure, M, key takeaways. Short columns fail by crushing, long columns by buckling. Biaxial bending requires interaction methods, Bressler's. Interaction diagrams simplify column design checks. Illustrations and examples. 1. Diagram, interaction curve for a rectangular column. 2. Flowchart, column design process, axial, uniaxial, biaxial. 3. Case study, design of a biaxially loaded column. Would you like a worked example on column design? Let me know how to refine this further. Chapter 7, Design of Reinforced Concrete Foundations. Foundations transfer structural load safely to the ground. This chapter covers shallow foundations, isolated, combined, raft, and deep foundations, pile caps, with design methodologies as per IS 456, ACI 318, and Eurocode 7. 7.1 Isolated and combined footings. 7.1.1 Isolated footings, used for single columns with uniform soil pressure. Design steps: 1. Calculate loads, /p_u equals 1.5, dl plus ll, /quad, /text factored load, /2. Determine footing area, a equals /frac p_service sbc /quad, /text sbc equals safe bearing /3. Check for punching shear, // tau v equals /frac v ub 0 d lec tau c quad, text is 456, /4. Reinforcement design, bending moment, /m u equals /frac w ul quad, text cantilever action, steel area, capacity, a st equals frac m u 0.87 f y, d, 0.42 x u, /7.1.2 combined footings, used for, adjacent columns, when isolated footings overlap. Types, rectangular, for two columns with moderate load difference. Trapezoidal, for unequal column loads near property lines. Design approach, ensure CG of loads aligns with footing CG. Design as an inverted beam with upward soil pressure. 7.2 Raft foundation 7.2.1 When to use. Low SBC soils or highly uneven loads. Prevents differential settlement in weak soils. 7.2.2 Design methodology 1. Soil pressure check, /q equals /frac /sum pa /pm /frac m xyi x /pm /frac m yxi y 2. Finite element analysis, via for complex rafts. 3. Reinforcement, top and bottom mesh to resist bending. Thickness, 300-600 mm, depends on spans. 7.3 Pile caps and deep foundations 7.3.1 Pile foundations, used for, very weak soils or high-rise buildings. Pile cap function, transfers column load to piles. 7.3.2 Pile cap design 1. Truss analogy method, piles act as supports, cap as a deep beam. Tension tie, steel /t equals /frac n2d, s, 0.5 a p, where s equals pile spacing, a p equals column width, 2. Bending method, treat as flat slab supported on piles. 7.3.3 Special cases, eccentric loads, check for overturning. Group piles, efficiency reduction due to soil interaction. Key takeaways: isolated footings for stable soils and single columns. Combined footings when columns are close. Rafts distribute loads uniformly in weak soils. Pile caps transfer loads to deep, stable strata. Illustrations and examples 1. Flowchart, foundation selection based on soil and load. 2. Case study, raft foundation for a high-rise building. 3. Comparison, isolated versus combined footing designs. Would you like a worked example on pile cap design? Let me know how to refine this further. Chapter 8, Design of Reinforced Concrete Staircases. Staircases are critical structural elements that require careful design for safety, durability, and serviceability. This chapter covers types of staircases, load analysis, and reinforcement detailing. Per is 456, ACI 318, and Eurocode 2. 8.1 Types of staircases. 8.1.1 Based on structural behavior. Type description: best for simply supported on beams/walls at both ends. Residential buildings. Cantilever embedded into a wall on one side. Architectural aesthetics. Continuous multiple spans with intermediate supports. Commercial complexes. Helical, spiral, curved design around a central axis. Luxury spaces, atria. 8.1.2 Based on geometry, dog-legged, 2 flights with a half landing, most common. Open well, central gap between flights, for ventilation/light. Quarter turn/L-shaped, 90 degrees direction change. 8.2 Structural analysis and reinforcement details. 8.2.1 Load calculation. 1. Dead load, DL, self-weight of waste slab, steps, and finishes. \DL equals 25 \text kn/m superscript 3 \times \text thickness plus \text flooring 12 kn/m superscript 2 \2 live load LL 35 kn/m superscript 2 residential 57 kn/m superscript 2 public 3 factored load WU \W_U equals 1.5 DL plus LL \8.2.2 bending moment analysis for simply supported stairs \M_U equals \frac W_UL28 where \L equals horizontal span. For continuous stairs, use moment coefficients is 456, table 12. 8.2.3 Reinforcement design 1. Main bars, a long span \A_ST equals \frac M_U 0.87 F_Y, D, 0.42 X_U, minimum steel, \0.12 times BD for FE 415. 2 distribution bars, provide \0.15 times BD transverse to main bars. 8.2.4 Detailing requirements, anchorage, bars anchored into supporting beams/walls, \L_D \. Cranked bars, used at turning points, landings. Cover, 20 mm, mild exposure, 30-50 mm, severe exposure. 8.3 Special considerations 8.3.1 Deflection control, span/depth ratio, \frac LD \lec 25 \quad, \text simply supported, \8.3.2 Crack control, maximum spacing, main bars, \lec 3D or 300 mm, whichever is smaller. 8.3.3 Vibration, natural frequency, should exceed 5 Hz to avoid discomfort. Key takeaways Dog-legged stairs are most economical for residential buildings. Main bars resist bending, distribution bars prevent cracking. Anchorage and cover are critical for durability. Illustrations and examples 1. Diagram, reinforcement layout for a dog-legged staircase. 2 Case study, helical staircase design using software, tab/safe. 3 Table, comparison of stair types, cost, span, suitability. Would you like a worked example for a simply supported staircase? Let me know how to refine this further. Chapter 9, Prestressed Concrete Basics. This chapter introduces the fundamentals of prestressed concrete, covering its principles, advantages, and methods, pre-tensioning versus post-tensioning. 9.1 Introduction to Prestressing. 9.1.1 Concept of prestressing, definition. Prestressing involves introducing internal stresses in concrete before service loads to counteract tensile stresses during use. Key principle, \sigma_text final equals \sigma_text prestress, \sigma_text load \0 quad, \text no tension in concrete, \9.1.2 Advantages over conventional RC. Reduced cracking, improved durability. Longer spans with shallower sections. Lighter structures, less material usage. Better fatigue resistance. 9.1.3 Materials, concrete, high strength, \F_CK \G35 \text MPA Tendons, high tensile steel wires, \F_P \G 1500 \text MPA Duct/grout, for post-tensioning corrosion protection. 9.2 Pre-tensioning versus post-tensioning. 9.2.1 Pre-tensioning, process, 1 Tendons are tensioned before casting concrete. 2 Concrete is poured and cured. 3 Tendons are released, transferring stress to concrete via bond. Applications: precast elements, beams, slabs, railway sleepers. Factory production, better quality control. 9.2.2 Post-tensioning, process. 1. Concrete is cast with ducts for tendons. 2. After curing, tendons are tensioned and anchored to the concrete. 3. Ducts are grouted for corrosion protection. Applications: bridges, large span buildings, nuclear containment vessels. 9.2.3 Comparison parameter: pre-tensioning, post-tensioning tensioning stage before casting, after casting, tendon bond, bonded, grouted, or unbonded side work, mostly prefab, cast in situ or segmental, span range short to medium, 1030 m, medium to long, 2100 plus m. 9.3 Losses in pre-stress. 9.3.1 Immediate losses, elastic shortening, concrete compresses during stressing. Friction, post-tensioning loss along curved ducts. Anchorage slip, wedge seating at anchors. 9.3.2 Time-dependent losses, creep and shrinkage, long-term concrete deformation. Relaxation, tendon stress reduces over time. Total loss calculation is 1343 text total loss approximate 1525 text of initial pre-stress key takeaways: pre-tensioning, factory-based, bonded tendons, shorter spans. Post-tensioning, on-site flexibility, and bonded, longer spans. Pre-stress losses must be accounted for in design. Illustrations and examples. 1. Diagram, stress distribution in pre-stressed versus RC beams. 2. Case study, pre-stressed concrete bridge construction. 3. Table, typical pre-stress losses in pre versus post-tensioning. Would you like a worked example on calculating pre-stress losses? Let me know how to refine this further. Chapter 10, Seismic Design of Reinforced Concrete Structures. This chapter covers the principles of earthquake-resistant design, focusing on ductility, detailing, and code provisions, is 13920 and ACI 318, to ensure structural safety during seismic events. 10.1 Ductility and detailing requirements. 10.1.1 Importance of ductility. Ductility, ability of a structure to undergo large deformations without collapse. Why? Earthquakes induce cyclic inelastic deformations. Ductile structures absorb energy. 10.1.2 Key detailing practices. 1. Beam column joints, confined concrete, closed hoops at joints. Anchorage, bars bent into the joint core, no straight pull out. 2. Beams, hoop spacing, \lec \frac d4 quad text or quad 100 text quad text, whichever is smaller, per is 13920, avoid lap splices in plastic hinge zones. 3. Columns, special confining reinforcement, hoops at less than or equal to 75 mm spacing near ends, plastic hinge zones. Minimum steel, 0.8% of cross-section. 10.2 Code provisions, is 13920 versus ACI 318. 10.2.1 is 13920, Indian Standard, Scope, Ductile detailing of RC structures in seismic zones, Zone 3B. Key rules: strong column, weak beam, \some m underscore column \gc 1.1 some m underscore beam shear capacity, design shear force equals 1.4 times calculated shear, to account for overstrength. Stirrups, 135 degrees hooks with 10D extensions, for hoop anchorage. 10.2.2 ACI 318, American Standard, Chapter 18, Special Moment Frames, SMF, and Shear Walls. Key differences from IS 13920, Transverse Reinforcement, Spacing, lec frac h4 or 100 mm, similar but stricter for SMF. Development length, bars in tension zones require 1.25 times basic development length. 10.2.3 Comparison table parameter is 13,920 ACI 318 hoop spacing frac D4 or 100 mm frac H4 or 100 mm shear design 1.4 times calculated shear over strength factor, omega equals 2.5. Lap splices not allowed in plastic hinges allowed with spiral confinement. 10.3 Special considerations 10.3.1 Soft story mitigation, problem, weak ground floors, e.g., open parking, collapse first. Solution, increase stiffness, shear walls, bracing. Avoid discontinuities in vertical load paths. 10.3.2 Shear walls, design rules, boundary elements, confined reinforcement at edges. Minimum thickness, 150 mm, is 13,920, or 200 mm, ACI 318. Key takeaways: ductility prevents brittle failure during earthquakes. Is 13,920 mandates tighter hoops, no lap splices in hinges. ACI 318 focuses on overstrength factors and SMF detailing. Illustrations and examples. 1. Diagram, proper detailing of beam column joints, hoops, bent bars. 2. Case study, retrofitting a soft story building post-earthquake. 3. Flowchart, seismic design process, capacity design detailing. Would you like a worked example on calculating shear reinforcement per is 13,920? Let me know how to refine this further. Chapter 11, Durability and Sustainability in Reinforced Concrete. This chapter explores long-term durability challenges and sustainable practices in reinforced concrete design, focusing on corrosion prevention, high-performance materials, and eco-friendly technologies. 11.1 Corrosion Protection. 1.1.1 Causes of corrosion, carbonation, CO penetrates concrete, reducing alkalinity, pH 9. Chloride attack, common in marine environments or de-icing salts. Stray currents, from nearby electrified systems, e.g., railways. 1.1.2 Prevention methods. 1. Design measures, adequate cover, greater than or equal to 40 mm for severe exposure, per is 456. Low W/C ratio, less than or equal to 0.4, to reduce permeability. 2. Materials, epoxy-coated rebars or stainless steel. Corrosion inhibitors, e.g., calcium nitride. 3. Cathodic protection, sacrificial anodes, e.g., zinc, or impressed current. 11.2 High-performance concrete, HPC, 1.2.1 Key properties, compressive strength, 6150 MPa. Durability, low permeability, high chemical resistance. 1.2.2 Composition component role example silica fume fills micropores, increases strength 5-10% of cement weight. Superplasticizers reduces W/C ratio without losing workability. Polycarboxylate ethers fly ash/GGBS reduces heat, improves long-term strength 20-50% cement replacement. 1.2.3 Applications, bridges, high-rises, nuclear containment structures. 11.3 Green concrete technologies. 1.3.1 Sustainable materials. 1. Recycled aggregates, from demolished concrete, up to 30% replacement. 2. Geopolymer concrete, cement-free binder, fly ash and alkali activator. CO reduction, 80% versus OPC. 1.3.2 Carbon capture concrete, carbon cure, injects CO during mixing, mineralizing it into the matrix. 1.3.3 Self-healing concrete, methods, bacteria-based, e.g., Bacillus pseudofermis precipitates calcite. Microcapsules, release healing agents when cracks form. Key takeaways: corrosion protection requires good design, materials, and coatings. HPC enables stronger, longer-lasting structures. Green concrete reduces carbon footprint via recycled materials and new binders. Illustrations and examples. 1. Diagram: corrosion mechanism in carbonated versus chloride exposed concrete. 2. Case study: Burj Khalifa's HPC mix, silica fume and superplasticizers. 3. Table: comparison of conventional versus geopolymer concrete. Would you like a worked example on calculating concrete cover for marine exposure? Let me know how to refine this further. Next steps, link to Chapter 12, Repair and Retrofitting, for corrosion-damaged structures. Explore software tools, e.g., LIFE365 for corrosion modeling. Chapter 12, Repair and Retrofitting of Reinforced Concrete Structures. This chapter covers common defects in RC structures, diagnosis methods, and modern strengthening techniques like FRP, fiber-reinforced polymer, and jacketing to restore or enhance structural capacity. 12.1 Common defects and failures. 2.1.1 Material-related defects: cracking, due to shrinkage, overload, corrosion. Spalling, broken concrete exposing rebars. Honeycombing, poor compaction during casting. 2.1.2 Structural failures: shear cracks, diagonal cracks in beams/columns. Flexural failures: excessive deflection, bottom cracks in beams. Punching shear, slab failures around columns. 2.1.3 Non-destructive testing, NDT, for diagnosis method purpose. Rebound hammer estimates concrete strength. Ultrasonic pulse velocity, UPV, detects voids/cracks. Half cell potential checks rebar corrosion activity. 12.2 Strengthening techniques. 2.2.1 Fiber reinforced polymer, FRP, wrapping, materials, carbon, CFRP, glass, GFRP, or aramid fibers. Process: 1. Surface preparation, cleaning, rounding edges. 2. Apply epoxy adhesive. 3. Wrap FRP sheets around the member. Advantages: high strength to weight ratio. No additional dead load. Corrosion resistant. 2.2.2 Steel/concrete jacketing, steel jacketing, 4, columns, beams. Method: weld steel plates around the member, fill grout. Concrete jacketing, 4, columns, walls. Steps: 1. Roughen existing surface. 2. Add shear keys/dowels. 3. Cast new concrete with additional rebars. 2.2.3 External post-tensioning, used for bridges, slabs. Method: install high-strength tendons outside the member and stress them. 2.2.4 Comparison of techniques. Method best for limitations. FRP wrapping beams, columns. UV degradation, needs coating, steel jacketing. Heavy loads, corrosion risk. Concrete jacket columns, walls adds weight, space. Key takeaways: diagnose defects using NDT before selecting a repair method. FRP is lightweight and versatile but costly. Jacketing is robust but increases member size. Illustrations and case studies. 1. Diagram: FRP wrapping steps for a corroded beam. 2. Case study: seismic retrofitting of a school building using concrete jackets. 3. Table: cost versus effectiveness of FRP versus steel jacketing. Would you like a worked example on designing an FRP wrap for a damaged column? Let me know how to refine this further. Next steps, link to Chapter 10, Seismic Design, for retrofitting in earthquake zones. Discuss monitoring systems, sensors for post-repair performance. Chapter 13, Detailing of reinforcement in RC structures. This chapter covers critical aspects of reinforcement detailing, including bar bending schedules, BBS, anchorage and splicing, ensuring compliance with IS 456, ACI 318, and Eurocode 2-13.1 bar bending schedules, BBS, 13.1.1 Purpose of BBS, standardizes reinforcement cutting and bending. Minimizes waste by optimizing bar lengths. Ensures compliance with design drawings. 13.1.2 Key components of BBS column description example bar mark unique ID for each bar type, e.g., B1, B2, B1 main beam bottom bar DIA, bar diameter 12, 16, 20 shape code indicates bend type, as per IS 2502, stirrup, code 05, cutting length total length before bending bent length after bending 4500 mm 5000 mm, with hooks, 13.1.3. Sample BBS for a beam bar mark DIA, shape code no of bars cutting length, total length, B116 straight for 6024.0 ST18 code 05 21224.0-13.2 anchorage and splicing 13.2.1 anchorage length, L, purpose, ensures force transfer between steel and concrete. IS 456 formula, /L_D equals /frac /phi .0.87 F_Y4 /tau_BD /phi equals bar diameter, /tau_BD equals design bond stress, e.g., 1.2 MPa for M20 concrete, 13.2.2 hooks and bends, standard hooks, 180 degrees hook equals /4 /phi extension plus /16 /phi bend radius. 90 degrees hook equals /12 /phi extension. Example, for a 12 mm bar, 180 degrees hook length equals /4 times 12 equals 48 millimeter 13.2.3 lap splices, types, contact lap splice, bars overlap directly, most common. Non-contact splice, bars spaced less than or equal to /150 millimeter, minimum lap length, is 456 /L_lap equals L_D /quad /text or /quad 30 /phi /quad. /text whichever is larger, /13.2.4 staggered splices, rule, splices should be offset by greater than or equal to 0.3 L to avoid weak planes. 13.3 Practical detailing rules 13.3.1 Beam detailing, main bars, extend into supports greater than or equal to /L_D stirrups, spacing, /lek /frac D2 or 300 mm, whichever is smaller. 13.3.2 Column detailing, lap splices, located in the middle half of the column height. Helical ties for confinement in seismic zones. 13.3.3 Slab detailing, minimum reinforcement, /0.12 of gross area for FE 415. Cranked bars, used near supports to resist negative moments. Key takeaways: BBS ensures accurate reinforcement fabrication and reduces waste. Anchorage length prevents bond failure. Lap splices must meet code-specified lengths. Illustrations and examples. 1. Diagram, standard hook dimensions, 180 degrees, 90 degrees. 2. Case study, BBS for a residential building slab. 3. Table, lap lengths for different bar diameters, is 456 versus ACI 318. Would you like a worked example on calculating lap length for a 16 mm bar in M25 concrete? Let me know how to refine this further. Next steps, link to Chapter 14, software in RC design, for automated BBS generation. Discuss common site errors, e.g., insufficient lap length. Chapter 14, Use of software in reinforced concrete design. This chapter explores industry standard structural software, ATABS, STD.Pro, SAFE, and BIM integration for efficient RC design, analysis, and collaboration. 14.1 Popular RC design software. 14.1.1 ATABS, developed by CSI, Computers and Structures, Inc., primary use, analysis and design of high-rise buildings. Seismic and wind load simulations. Key features: integrated slab, beam, column, and shear wall design. 3D finite element modeling. Compliance with ACI, IS, Eurocodes. 14.1.2 STD.Pro, developed by Bentley Systems, primary use, industrial structures, tanks, bridges, towers. Geometric nonlinearity, e.g., cable structures. Key features: supports concrete, steel, timber, and aluminum. Open API for customization. 14.1.3 SAFE, developed by CSI, primary use, slab and foundation design, raft, mat, pile caps. Punching shear checks. Key features: soil structure interaction analysis. Post-tensioning design tools. 14.1.4 Software comparison. Software best for limitations ATABS high rises, RC frames less suited for infrastructure. STD.Pro bridges, plants steeper learning curve. SAFE foundations, slabs only for horizontal systems. 14.2 BIM applications in RC design. 14.2.1 What is BIM? Building information modeling, BIM, a 3D digital twin integrating geometry, materials, and project data. 14.2.2 BIM software for RC1. Revit and robot structural analysis, Autodesk, design integration, sinks architectural and structural models. Rebar detailing, automatic bar placement. 2 Tekla structures, precast concrete modeling. Clash detection, avoids reinforcement conflicts. 14.2.3 Benefits of BIM in RC: reduces errors, e.g., rebar clashes. Improves collaboration, architect left and right arrow, engineer left and right arrow, contractor. 4D/5D BIM, adds time and cost tracking. 14.3 Workflow integration. 14.3.1 Typical design process. 1. Modeling, ATABS/STD for analysis. 2. Detailing, Revit/Tekla for reinforcement. 3. Documentation, AutoCAD for shop drawings. 14.3.2 Cloud collaboration, platforms, BIM 360, Trimble Connect. Use case real-time updates across teams. Key takeaways: ATABS dominates high-rise RC design, STD.Pro for infrastructure. BIM minimizes construction errors via 3D coordination. SAFE specializes in slabs/foundations. Illustrations and case studies. 1. Screenshot, ATABS seismic analysis of a 20-story building. 2. Workflow diagram, BIM integration from design to construction. 3. Table, software cost versus capabilities. Would you like a step-by-step tutorial for modeling a simple RC frame in ATABS? Let me know how to refine this further. Next steps, link to Chapter 15, Case Studies, for real-world software applications. Discuss AI in structural design, e.g., generative design tools. Chapter 15, Case Studies and Real-World Examples in RC Design. This chapter presents real-world applications of reinforced concrete design in residential buildings, bridges, and industrial structures, highlighting design challenges, solutions, and lessons learned. 15.1 Residential buildings. 15.1.1 High-rise apartment complex, Mumbai, India, project, 40-story residential tower in seismic zone 4. Challenges: high wind and seismic loads. Limited space for foundations. Design solutions, dual system, shear walls and moment-resisting frames. Pile raft foundation, 2 m thick, to distribute loads. IS 13920 compliance, special confinement at beam column joints. Software used, A tabs for analysis, safe for foundation design. 15.1.2 Affordable housing, Ethiopia, is 456 based, project, 500 unit low-cost housing. Innovations, prefabricated RC panels for rapid construction. Geopolymer concrete, reduce CO emissions. 15.2 Bridges 15.2.1 Cable stayed bridge, Vietnam, span, 250 m main span, post-tensioned concrete pylons. Key features, segmental construction to avoid false work over river. Durability focus, silica fume concrete and cathodic protection. 15.2.2 Railway overpass, Germany, Eurocode 2, challenge, heavy dynamic loads from high-speed trains. Solution, fiber-reinforced concrete, steel fibers for crack control. Continuous monitoring with embedded sensors. 15.3 Industrial structures 15.3.1 Nuclear containment vessel, France, design standard, ACI 349, nuclear facilities. Critical elements, 1.2 m thick prestressed walls, post-tensioned. Leak tightness, multiple liner plates. 15.3.2 Cement plant silo, USA, ACI 313, issue, cyclic thermal loading causing cracks. Retrofit, carbon FRP wrapping, 10 layers. Stainless steel rebar in new construction. Key lessons from case studies. Residential, shear walls and proper detailing save lives in quakes. Bridges, pre-stressing enables long spans, durability is critical. Industrial, special codes, e.g., ACI 349, govern extreme environments. Illustrations and data 1. Photos, crack patterns in retrofitted versus original silo walls. 2. Graph, seismic performance comparison of dual versus frame systems. 3. Table, cost breakdown for conventional versus prefab housing. Would you like detailed calculations for the cable-stayed bridge pylon design? Let me know how to refine this further. Next steps, link to Chapter 12, Retrofitting, for repair case studies. Explore sustainability metrics, e.g., CO savings in geopolymer concrete. Appendices. This section provides quick reference tools for reinforced concrete design, including design aids, sample calculations, and code summaries. Appendix A, design tables and charts. A.1 Material properties. Material property value, is 456, value, ACI 318, M25 concrete /F_CK MPA, 2525, 4000 psi, FE 415 steel /F_Y MPA, 415 60 KSI, A.2 span / depth ratios for deflection control member simply supported continuous beams 2026 slabs 2535 A.3 development length, L, 4 FE 415 billion Argentine pesos bar DIA, mm, M20 concrete, mm, M25 concrete, mm, -12 470 416 630 530 Appendix B, sample calculations. B.1 Singly reinforced beam design, is 456, given, /m_u equals 120 /text knm /b equals 300 /text mm d equals 450 /text mm f_ck equals 25 /text mpa backslash, F underscore Y equals 415 backslash text MPA backslash. Steps, 1 check backslash, M underscore U lim equals 0.36 backslash dot F underscore CK backslash dot B backslash dot X underscore U backslash dot D, 0.42 X underscore U, equals 145 backslash text KNM backslash. 2 since backslash, M underscore U lim backslash, design as singly reinforced. 3 calculate backslash, A underscore ST equals backslash frac 120 backslash times 1060.87 backslash times 415 backslash times 450 to 0.42 backslash times 0.48 backslash times 450 equals 800 backslash text superscript 2 backslash. B.2 punching shear check for flat slab, ACI 318, given, column load backslash, P underscore U equals 1500 backslash text KN backslash, slab thickness backslash, T equals 200 backslash text backslash, backslash, F underscore C equals 30 backslash text MPA backslash. Steps, 1 critical perimeter backslash, B underscore 0 equals 4 backslash times, 400 plus D, equals 2400 backslash text backslash. 2 shear stress backslash, backslash tau underscore V equals backslash frac 1500 backslash times 10 2400 backslash times 180 equals 3.47 backslash text MPA backslash. 3 permissible stress backslash, backslash tau underscore C equals 0.33 backslash SQRT F underscore C equals 1.8 backslash text MPA backslash text shear reinforcement needed backslash. Dash Appendix C, Important Code Clauses C.1 is 456:2000, Clause 26.5, Minimum Reinforcement, 0.12% for beams, 0.15% for slabs. Clause 34.4, Punching shear provisions. C.2 ACI 318-19, Table 2 1.2.1, Strength Reduction Factors, backslash phi equals 0.9 backslash, for flexure. Chapter 18, Special Moment Frames. C.3 Eurocode 2, and January 1, 1992, Section 7.3, Crack width limits, 0.3 mm for normal environments. Dash Appendix D, Glossary of terms term definition ductility ability to deform without brittle failure. LSBC development length for rebar anchorage. Safe bearing capacity of soil, Kn/m superscript 2. Dash references and further reading 1. Is 456:2000 Indian standard for plain and reinforced concrete. 2 ACI 318-19 Building Code requirements for structural concrete. 3 Eurocode 2, and January 1, 1992, Design of concrete structures. 4 Park and Pauli reinforced concrete structures, theory. 5 Neville and Brooks concrete technology, material science. Dash how to use this appendix design tables, for quick checks during preliminary design. Sample calcs, validate software outputs manually. Code clauses, ensure compliance during audits. Would you like additional tables for pre-stressed concrete or seismic design? Let me know.